Welcome back. Imagine the absolute chaos of completely unorganized data. Literally, picture a massive warehouse with no labels, no shelves, and just endless, indistinguishable boxes everywhere. Today, we're going to tame that chaos. We're diving into the intricacies of logical database design, and really framing it as the ultimate translation. We're taking a high-level conceptual blueprint of that messy warehouse and turning it into a rigorous, physical-ready language that a computer system can actually rely on. I'm your host, and this is our explainer on building the logical data model. Let's get into it.
Okay, so here's our roadmap for today's explainer. We're breaking this down into 5 distinct phases: translating concepts to relations, validating your relational schema, protecting data with constraints, merging multiple user views, and finally, future-proofing the database.
Let's jump right into Phase 1, translating concepts to relations.
So what exactly are we building here? Well, a logical data model is essentially a model of the data used in an enterprise based on a specific data model, in our case, the relational model. But the absolute crucial thing to remember is that it remains completely independent of any particular database management system. Think of it like a mathematical bridge, right? It connects human concepts like employees and departments to the actual machine that will eventually store the data. It's all about establishing the structure way before we ever worry about the specific software.
To cross that bridge, we have to follow some pretty strict mapping rules. For a strong entity, it's simple. We just create a new relation or a table and include all of its simple attributes. But when we hit one-to-many relationships, well, that's where the real magic of database structure happens. We like to use a parent and child analogy here. The entity on the one side becomes the parent, and the many side becomes the child. To link them up, we just post a copy of the parent's primary key into the child relation to act as a foreign key. It's kind of like giving the child a genetic marker so we always know exactly who the parent is.
Now things get really interesting when we encounter one-to-one relationships. It's not just about counting, it's actually about participation constraints. If participation is mandatory on both sides, say every single client must have exactly one preference profile and vice versa, we just combine them into one single relation. Honestly, why keep them apart? But if it's mandatory on only one side, the entity with optional participation actually becomes the parent and the mandatory entity becomes the child. It is totally fascinating how a simple business rule directly dictates exactly where our mathematical foreign keys are going to live.
Moving right along to Phase 2, validating your relational schema. At this point, we really have to stop and ask ourselves, is our structure actually sound? I mean, sure, we mapped out relations, and they look perfectly logical on paper, but can they survive real-world data processing without duplicating data or causing massive update errors? To answer that, we bring in normalization. This is our ultimate stress test. The goal here is to ensure we have a minimal yet sufficient number of attributes. We want to ruthlessly remove data redundancy. Why? To avoid update anomalies. You know, those absolutely terrifying moments where changing a customer's address in one place leaves their old address active in 3 other tables, creating total inconsistency. So the bottom line is, we must test our schema until it achieves at least third normal form, or 3NF. This guarantees that our architecture is lean and totally free of those dangerous anomalies.
But hey, mathematical perfection alone just isn't enough. We have to prove its real-world value. We do this by manually validating the schema against the required user transactions. It's a simple 3-step process. Step 1, you review the relations and your data dictionary. Step 2, you attempt to perform the expected user transactions manually, literally on paper. Like, if a user needs to find all properties managed by a specific staff member at a certain branch, can you actually trace that exact path through your primary and foreign keys? And step 3, if a transaction fails, your structure is flawed and you got to go back and resolve it. It's a critical reality check for your design.
All right, Phase 3, protecting data with constraints.
To maintain order, we absolutely need integrity constraints. These are high-level rules to protect the database from becoming incomplete, inaccurate, or just plain inconsistent. The interesting thing is, at this stage of the logical design, we only care about what rules are needed. We completely ignore how the specific database software might eventually implement them. We are basically establishing the universal law of the land for our data.
A massive part of this law is referential integrity. Specifically, what happens if we try to delete a parent record that still has connected child records? Well, there are 4 vital strategies here. No action outright prevents the deletion from the parent relation if there are any referenced child tuples. Cascade automatically deletes all the referenced child tuples too. Now be very careful with Cascade. Misusing it could result in accidentally wiping out massive amounts of important data. Imagine firing a staff member and accidentally deleting all the rental properties they manage from your entire system. No way. Then we have set null, which blanks out the foreign key indicating the new status is unknown, or set default, which might reassign those properties to a default manager. Choosing the right strategy here is a total game changer for data protection.
Let's transition to Phase 4, merging multiple user views.
In a massive enterprise, different departments see the business totally differently. So we have to differentiate between local and global models. A local logical data model represents just a piece of the puzzle, one or two user views. But the global logical data model represents all user views merged together into a single cohesive unit. View integration is absolutely necessary to create a single source of truth for the entire enterprise. Without it, you just end up with fragmented, overlapping data silos that constantly contradict each other, and nobody wants that.
But I gotta warn you, merging models is an absolute minefield of linguistic pitfalls. We primarily battle two enemies of integration: homonyms and synonyms. Homonyms are when items have the exact same name but completely different meanings. For example, the relationship manages might mean a staff member managing a rental property in one view, but a supervisor managing a branch in another. Synonyms are the exact opposite. Different names, but the same meaning, like one department saying staff and another saying employee. If left unchecked, these naming conflicts will literally cause total chaos when you try to merge your models.
To conquer this chaos, we use a highly systematic merging process. First, we rigorously review names and contents across the models. Then, we merge equivalent entities, usually spotting them pretty easily because they share the exact same primary key. Next up, we include the unique, non-overlapping views without altering them at all. And finally, we double-check our global integrity constraints and foreign keys to ensure the newly merged architecture holds together perfectly. This step-by-step approach prevents data loss and safely resolves overlaps. It essentially turns a massive headache into a totally solvable puzzle.
And that brings us to our final section, Phase 5, future-proofing the database.
The holy grail of this phase is achieving what our source material calls a true and accurate representation of the data requirements of the enterprise. Listen, you can mathematically validate your schema all day long, but you can only verify this ultimate truth by actually sitting down and reviewing the logical model with the users themselves. If they are satisfied that it captures their daily realities and business rules, well, then your model truly represents the enterprise.
But the enterprise will inevitably change, right? So I want to leave you with this provocative question as we wrap up this explainer. Can your freshly built, perfectly translated, and rigorously stress-tested data model actually survive the unknown future? Is it extensible enough to accommodate tomorrow's growth, new departments, and completely shifting business rules, all with minimal impact on existing users? A truly great database designer doesn't just design for today's transactions, they design a logical structure robust and flexible enough to welcome whatever comes tomorrow. Thanks for tuning in to this explainer. Keep analyzing, keep structuring, and we'll see you next time.